I'm very happy to come here. And I apologize. I apologize to everyone because I didn't provide my title and abstract until yesterday. Actually, I was thinking what I should talk, but yesterday Bertrand I decided on title. I have already talked about this topic many times. Maybe half of you have already heard my results. So the other part doesn't contain new results, but I think it should be good to recall what I'm doing because half of the participants are not familiar in topological. So anyway, yeah. So actually today I will talk about basically two topics. One is construction of a function for one equation by topological recursion. It has already the result is already in 50-year-old. And also, I will try to make some comment about the relation to the irregular conformal block, which is within a recent preprint by here and anyway, so my talk is also related to some topological intersection of the topological recursion and irregular conformal blocks. But the Bertrand and I explain this relation by saying that so TR can solve certain but actually, so I will in this talk I will try to explain the relation between CFT and topological recursion by some special function from the view, so mainly on the Painleve equation. To start, okay, so let me start by explaining some relation between topological recursion and the special functions. Namely, the so-called quantum curve machinery. I'm not explaining some general theory, but let me focus on some examples. So the first example is the so-called Airy's equation, or Airy spectral curve, so which is, do you remember, so topological recursion is some machinery, so if you give some spectral curve, which is a polynomial algebraic curve defined by certain equation, then you can provide some certain correlators. And in this case, to run the topological recursion, so we can parameterize this one and a triplet. And actually, so this curve is a genus 0, so we don't have to take some fixed summatory marking, but yeah. Anyway, so then, so as Bertrand explained, so this X can be regarded as some branch covering of the base P1, so which is P1. Recursion is some recursive machinery which provides some multi-differential, melodic multi-differential defined on this sigma. And as Bertrand explained, so the omega 01 is y dx. And explicitly in this case, to b squared dz. So it has a pole at infinity. And the pole is not simple pole, so actually this is non-Hookean example, which means irregular. It has a irregular singularity. And omega 02, which is a bi-differential. And this is genus 0, so this is a canonical choice. So, so this appears in the Bertrand's talk here. So this is 2, and this is a bi-differential, which has a double polar of the diagonal with pi raised to 1. And omega 03, omega, so in general, topological recursion, so unfortunately, the general definition has not appeared in this factor. So this is the general formula which I writing down. Yeah, so it has several notations, but first of all, so this is defined by some residue along some set R, and R is a so-called ramification point, so which is a 0 for Gx. And for Airy's example, so you can see that so it vanishes only at the origin, so this is just a single point. So you can take the residue at the origin, so R is just the origin. Q is some dummy variable to take some residue. And the sigma of Q is a so-called local involution. But in this case, so sigma of Q is given by minus Q, so which is some local, well, so in this case global, but anyway, so this is a covering involution of this spectral graph. So it fixes X, but changes the sign of Y. So this is some involution. It appears in space, and I'm not going to talk about the right hand side, but it has some complicated expression. But if you run the topological recursion, then sorry, I don't have enough time, but enough space. but the resulting formula is look like this. Z1 square, Z2 square, Z3 square is the denominator, and this is a tensor product of them. As Bertrand explained, so correlator can have a force along the diagonal at G equals 0, N equals 2, but others are singular only at the ramification point. This is a general structure. And actually, so this topological recursion correlator do have some relation to the differential equation. So this is the first remark. This was already known more than 10 years. It is proved by Jianzhou, but conjectured by Gukov and Tsikovsky. In the same year. So namely, so basically, so this correlator, so these correlators are some differentials, but you can take a primitive from a certain point. So in this case, it is natural to take infinity as a lower end point. But you have to subtract some, you have to regularize this one when G equals 0 and N equals 2. Okay. And sorry, so this is here. And after taking this, then you have some function, which and you diagonalize it. So actually, so this is a multi-valued function, but you can diagonalize it because we have collected in singular terms. And then you can switch the coordinate from Z to X. So in this case, Z to X is an inverse function of that. So depending on the of the branch, but basically to get square root of it. And you have some function which can have a branch point at X equals 0. But now you take the generating series. So G is running from 0 to infinity, and N is also running from 1 to infinity, and N factorial which is minus 2 plus N. You have the power series in H bar, whose coefficients are functions of X, and take its exponential. And define this as a psi, and it is called TR wave function. It is called a function, but it is a form of power series in H bar. And it is also, yeah. Anyways, claim is that so this is the so-called Wenzel Kramer-Brill one for WKB formal solution of the Airy's equation. Maybe this is very famous, but the Airy equation with small parameter H bar. And this H bar is appearing in above generating series. So this H bar is appearing in this way. And this is a relation between topological recursion and differential equation. And this is this resulting Schrödinger type of operator is some kind of quantization of this original spectral graph. So in this sense, so this topological recursion can be regarded as one of the ways to quantize the spectral curve. The original spectral curve is here. And actually, so TR is some quantization, and this is classical limit. Classical limit of the equation. And actually, so this gives some relation between topological recursion and differential equation. So I do not have time to give a proof, but so basically, you can translate this topological recursion relation into the recursion relation for the coefficient of this WKB expansion, and actually it is indeed agree with the WKB recursion coming from this Schrödinger equation. Yes. And actually, so this happens many examples. By the way, but before going to another example, so let me make one remark. As I explained, actually, so this is divergent in general. So this is just a formal solution. But at least if this quantum, by the way, so this Schrödinger type of operator is called quantum spectral curve. And in case if you obtain quantum curve as an ordinary differential equation, then actually we can use some machinery of the exact WKB. And it is known that these divergent solutions are more summable on some engineering equations. But I don't have time to explain about the Borel summation, but instead let me explain one thing. Actually, so Airy's differential equation has an exact solution. That is a divergent formal solution, but it has an exact solution, which is oscillatory integral of, say, what is better, u and x. And u is the integration variable, and this w is this polynomial in u, and x appears. So x is the independent variable with this Airy equation, appears in the parameter of this function. So it is kind of related to some unfolding of A2 singularity maybe. Yeah. And actually, so you can check that by the saddle point approximation. Approximation or expansion. You see for this phi. Maybe I forgot to mention. Okay, so you can so since the Airy equation is second order, so there are two independent formal solutions, and it is obtained by this. And actually, so you know, so this, so saddle point expansion requires, or so you have to look at some critical point of this functional, and which is the zero of this w. Then you have two critical points. And the critical value, corresponding critical value, is nothing but the plus or minus 3 to x. You have. And actually, so this is with the primitive of omega 01 evaluated at z of x. Because omega 01 is this, so primitive is z cube, equal to z cube, and z is square root of x, so this is nothing but this one. So plus or minus. Yeah. And anyway, so at least the, yeah. Anyway, so this is a correspondence between exact solution and divergent solution coming from the topological recursion. And in some sense, the Borel summation is an inverse operation. So once you have some divergent series, then so if you are lucky, so you can reproduce the original exact function by taking the, so which recover the original divergent series. So this is the standard for Borel summation procedure. Yeah. And actually, so in this situation, so you can. So there is an X plane. So then maybe you have seen this kind of figure many times. So there is a so-called notion of Stokes graph. It is also called spectral network. Yeah. So on X plane, so there are several non-Borel summable locus, which means that when X lies on one of the line, then this divergent series is not Borel summable as a H buffer series. And another way to figure out, so when X lies on this one of the lines, then the steepest descent path emanating from one of the critical points hits another critical point. So this, in this case, saddle point approximation breaks down, and yeah, some Stokes phenomenon happens. And this is one of the way to realize this topological recursion formal series as some exact function. But sorry, today I'm not going to talk about some details. And in general, the Borel summability of the topological recursion partition function or wave function is not established. But so this is very simple example, so we know the Borel summability and so on. Okay, so this is almost all to say about the Airy equation, but any questions or comments? Okay, then let me move on to the next example. Actually, so I have written down the point, but I will not use this anymore. Okay. The next example, I'm not sure if I have time, but let me try. So next example is hypergeometry. Or classical limit of the hypergeometric spectral graph. So it is known that this is the second order differential equation, which has a regular singular point at 1, 0, and 1 at infinity, so 3 functions. Regular singularity. 3 points on P1. And whose classical limit should be like this. Where is the square? Anyway, so these theta are some complex parameters related to some alpha, beta, gamma in hypergeometric functions. I parameterize this spectral curve in such a way that residue of y dx, so which is omega 01, at one of the singular points is this theta s up to psi. So this is a parameter, and maybe this is related to AI, it appears in Bertrand's talk. Yeah. And actually, so we are looking at, so basically, so WKB analysis for the hypergeometric mean that, so you know, we are descaling so this to F1 by alpha over h bar, beta over h bar, and gamma over h bar, and looking at the small h bar. In other words, we are looking at a large charge limit in this hypergeometric function. Yeah. Anyway, in that case, so theta zeros are related to this one of alpha, beta, gamma in certain way. Yeah. So anyway, so this is still theta zero curve, and topological recursion gives you similar things. Yeah. Actually, I will not write down the claim, but you can obtain this kind of theorem. So I mean, so if you take the generating series of the primitive of these correlators defined by topological recursion, then it solves the hypergeometric equation. In other words, you can obtain large charge expansion of the hypergeometric function from this topological recursion. And also, maybe it's also interesting to see that what is the Fg, which is omega g0. Some genus J contribution to the free energy. And interesting with some Bernoulli number here. Then the genus sub-index of G is greater than or equal to 2, 2G minus 2.
Excuse me, is it just true universally that the topological recursion series and WKB series is just the same thing?
It depends on the spectral curve. At least in a genus zero spectral curve, which is smooth, then I believe that WKB expansion produces the corresponding WKB solution of the ordinary differential equation. But we will see, in genus one spectral curve, the correspondence is a little bit subtle. We have to consider some partial differential equations instead of the ordinary differential equation. Maybe I will make some point. Yeah. And actually, here you have sorry, maybe I don't have to wait. So do you understand what I mean by so this is epsilon 1, epsilon 2 can be a both plus or minus. So it has 4 terms and also infinity to theta s to g minus 2. So this is a formula for the topological free energy. Yeah. Actually, this contains 7 terms with plus sign or minus sign. And actually, so it is, so these signs are related, so this number. So these are related to the so-called 4D BPS invariant in the sense of Kyle-Tomanai's case or Tom-Bridgiant in his study of the BPS structure. Yeah. Actually, so this was I observed with Oma-Kido-Y. And also related work is done by Kido-Y and Kento Osuga, and also Banerjee. In 5D case, so Banerjee and Alexander here, and Olivier Marshall, very recently. Maybe this preprint appeared in the last week, I think. In this case, so they studied 5D BPS instead of this body. Yeah. And also, actually, so this is also divergent because Bernoulli number grows factorially. But do you know what happens if you take the Borel summation of this Bernoulli series? So actually, the Borel sum of this Bernoulli series are given by band G function. Borel sum of Z the partial function for which is a generating series of 2G minus 2 Fg is given by up to some factor. So this is basically band G. Actually, so this kind of band G appears 4 times in the numerator and 3 times in the denominator. I think this is related to so-called DO formula. Yeah, time sample factor. And actually, so this Bernoulli number can be understood as a Starling expansion of these Banchi functions. Yeah. And I'm not giving some proof, but actually, so philosophically, so you can say that so actually, so these free energies are related to some kind of monodromy or connection data for the corresponding quantum curve. This is the hypergeometric equation. As you may know, so connection constant of the hypergeometric equation are written by gamma functions. So gamma gamma over gamma gamma is a connection constant. And actually, so this is related to the so-called Boros period in a framework of the exact WKB. And those Boros periods and the free energies are closely related. And in the end, we can obtain this kind of expression.
Maybe you can say this is DOZZ formula. This is DOZZ formula.
Yeah. At C equal 1 for it. So in usual topological recursion, it will be in this is always one. Any questions or comments? Anyway, I'm talking about some special function theoretic understanding about this formula.
Is this the same as DO double Z or?
Yeah, maybe this is better one. It's just same.
Just.
Yeah. So because this has, as I said, so this spectral curve is coming from the hypergeometric differential equation, which is rank 2 with some 3 regular singular points at 0 and 1 infinity. Okay, now let me move on the main example. So these are, so far we studied the CSL spectral curve, but so actually some relation to the Painleve equation and conformal blocks will appear in if we consider higher genus. Genus 1 spectral curve, so main example, which is Painleve 1.
Can I ask you something? So this factorization of the partition function has each term comes like from a singular point of the spectral curve, right? Where the spectral curve has a singularity, you get a contribution which at the end?
Yeah, that is for 3 terms.
Yeah.
But the other 4 terms are coming from different.
Yeah, there's some kind of mixture of them, right?
Yeah. So actually, so I don't have to explain, but if you look at the Stokes graph of this hypergeometric differential equation, then depending on your choice of the parameter, so there are several degenerations. So degeneration means, so in this case, actually, so this has a 2 ramification point, and not only that, so you have origin and 1 and infinity as a regular singular point on X plane. And basically, the Stokes graph is, maybe I have written some graphs here, which are just relates. So actually, so there are 3 curves emanating from each ramification point and form a graph on X plane. And this is the Stokes graph. And in some choice of the parameters, you will encounter this kind of finite Stokes segment, Stokes curve. And this is called the saddle connection. And for such a saddle connection is understood as some contribution of the BPS invariant in the work of Gautama-Naisuke. Actually, it is also related to the cluster transformation and so on. And for such a saddle connection, you can associate closed cycle on a spectral curve. So this is a picture in the base explained, but the spectral curve is double covering. There is a branch that's here. Yeah. And this cycle gives you, and this cycle, if you integrate ydx or omega 01 along the cycle, then you have either up to sign, so you have plus or minus or infinity. And actually, so these are corresponding, so these 4 terms are corresponding to such finite length saddle connections. And the other 3 are related to some saddle connection around the closed loop type saddle connection around one of the singularities. Yes. And then we move on. Okay. As I said, so let us consider genus 1 spectral curve. By the way, maybe in case if you do not know about the Painleve equation, so let me write down the formula. Q is the independent variable, T is the independent, and Q is the non-function. It is non-linear. And T, so this T will be this Painleve time, and this U will be fixed later. Yeah. And in this case, this is genus 1 spectral curve, so we have to fix the Torelli marking as Bertman explained. Yeah. I will consider some local. So this T and U are parameters, but I regard so they move on some very small circle, and on which we can see some marking about all the and impose as Bertrand did impose. After choosing the solid marking, I will take new parameter. So this is new, solid not B. And this is equal eta of I in Bertrand's talk. But anyway, so this is T independent. Then this defines some local family parameterized by this parameter T and nu. Yeah, so instead of this U, I use nu and T as a parameter for this basic curve. And then you can apply the topological recursion. Then you have omega gn and xg and so on. But in this case, so since the spectral curve depends on a parameter, so this becomes some function of those parameters, like in this case. So in this case, theta are contained in a parameter of the spectral curve, and it appears in this way, in the free energy. And similar thing happened in this. Then after this one, so I proved it. But later, soon later, so Bertrand A now, and Elba Garcia filed there in this room maybe. Yeah. And Olivier Marshall and Orantan. The thing is that if you consider the exact transformation, law. So I use the different parameter from the Bertrand talk and over H bar. And I prefer to use H bar depending shift. Yeah. And this Z is a partition function, which I have already erased maybe. Partition function is maybe I have written, but just in case. This is a generating series of FGs. And this one is usually denoted by total free energy F, and its exponential is called partition function. And as I wrote here, so this is the coefficient depending on nu. So I'm shifting nu by k times integer times h bar, and take the discrete Fourier series. Actually, so this is the divergent series, and so this discrete Fourier series looks like UD1, but actually, so there is a way to make sense of it. Other let me keep the details and here and denote this chart for some T1. To be more precise, so this is power some informal series in H bar in some sense, and coefficients are depending on T and mu, so which is an A period of the original spectral curve, and another parameter law coming from the discrete Fourier transformation or that transformation. The claim is that so this one is a formal series valued function of Painleve 1, so which is written there. And meaning, so this means that Q is obtained by logarithmic derivative of theta. If you write this series as some theta series, H bar series with some theta function coefficients, then you can make some sense here, and it solves. So this is the defining property of the tau function. Yeah, I think that this is the formal partially valid solution of the Kyoto type of biology.
But this is worse than formal power series. You have infinitely many negative.
Yes. But actually, so maybe okay, I can satisfy you, I think. So this Z is valid. Yeah, actually, this can be summed as a theta function.
The mathematical set where it belongs to, what is it?
It's something like this. It is some power series of H bar, and each coefficients are written by some kind of theta type of function, T, nu, rho. And unfortunately, the coefficient also depends on H bar.
And minus infinity, right? M.
No, this is only positive.
It's inside the theta function.
In the theta function, yes.
Ah, okay. I see.
Yeah. So actually,
But now you change like two summations, right?
yes,
Which is
this is just a formal exchange of the expansion. Yeah.
But you can calculate theta m's, right? From
Actually, for theta 0, leading term is identical to the original theta function without characteristic. But the argument of the theta function is something like b period of y dx plus rho divided by h bar. So this is the first argument of the theta function.
Ooh.
And so this 1 over h bar is coming from this, for example, Fourier current and so on. Or a second Taylor series coefficient of this partial function.
It is even worse than here.
But I like this. And tau of the. So this is modular. Second argument is the modulus of the elliptic curve, which is chosen in the beginning. Yeah. And higher order terms are written by some finite sum of the derivative of theta function. So it's like so thick, but I think it's a really good object. And this is also called non-perturbative function. Introduced much more earlier by Bertrand Einer and Marcos Marinho. Yeah. What I'm saying is that so this non-perturbative partition function is a tau function for the Painleve equation. Actually, so this is not only the case of Painleve 1, but also other Painleve equations by basically so 4 people. Yeah. I think so maybe it's better to explain why this kind of object can solve the Painleve equation. And maybe I will not give some explanation with details, but let me explain some philosophy why this can solve the Painleve equation. Why? So how to remark is that so if you define psi plus or minus of this spectral curve in the same way as written above, namely, so this is if you define psi plus minus as a PR wave function. And this first argument that it satisfies, actually I'm answering to one of your questions, satisfies the following partial differential equation. Which is second order in X, but contain first order derivative with respect to the time parameter t, and 2 times h bar square and partial derivative of h, which is a log of so this holds. Actually, so the leading term of this, so this is the h bar power series starting from h bar to the power 10, and its leading term is actually the pointer. It's pointer with the original spectral curve, but it has some infinite many h bar collections. And some h bar collection also coming from this term. So in this sense, so there is some gap between the WKB solution of the ordinary differential equation and the topological recursion wave function. And in genus zero situation, spectral curve is genus zero, then this is controllable, but in this case, so there are infinitely many. But still, we can control it by looking at the partial differential equation.
So, what's the relation between this psi plus 1 and the tau you had before?
I'm trying to construct some isomonodromic object which is related to the Painleve tau function by some Gimon-Miller type of argument. And I'm trying to explain, Anyway, so this is closely related to some solution of the isomonotomic linear differential equation in X variable. And actually, so this is somehow related to Belaville-Polyakov, the Monotochkov type of equation. Maybe you have seen some formula for the BDD equation, which is it is satisfied by conformal block with certain degenerate insertion. And X is the insertion point. So in this sense, this psi is somehow which is related to the conformal block with some degenerate insertion.
But BPC is an ODE, right?
No, I don't think so. It's a partial differential equation. So for example, if you consider the 4 points, they are so conformal block. 1, 2, 3, 4. And if you insert one more point, they satisfy some partial differential equation, I think, in all variables. And actually, so psi is somehow irregular version of this one is to be plus minus. So this is what I tried to do.
But this equation has no, by no means a unique solution, or.
Sorry, pardon me.
But it's not quite a dimensional space of solution. It's just
Actually, there
you
is
have no second equation.
no second equation. But there is some infinitely many solutions. But actually, there is some interesting property. The next important property of this psi plus or minus is a monodromic property. So this is a power series in H bar. I just erased, but it is a power series in H bar, but coefficients are function of X, and it is defined on a spectral curve. Since it is defined as a primitive of some differential form on a spectral curve, so it can have a monodromy along A cycle and B cycle. And if you compute the term-wise formal monodromy, term-wise analytic continuation along these A cycle and B cycle, then we see. So basically, actually, I'm computing some kind of Boros period of this series. And along the A cycle, so you have this one. So maybe it's better to emphasize what is the initial value of mu along A cycle. But actually, so this one will be shifted by plus or minus H bar along B cycle. And those two properties follow from some so-called variational formula in a topological recursion. Yeah. So anyway,
What is V?
B cycle, sorry.
No, V. What's the V?
Sorry, this
variable.
So this is sorry mu. Is the APU. Sorry. Yeah. And maybe I forgot to mention, but in a topological recursion, so maybe you have seen this kind of formula. So there is one by differential or omega 02 in a elliptic curve is given by various transfer function. But you have some D2-like term. And thanks to this D2 term, so this has a trivial A period. And it is by differential, but if you regard this as a differential in one of the variables, and you can integrate it along the A cycle, then it vanishes because of this constant term. And this normalization property along the A cycle inherits to all order coefficients, higher order coefficients. So non-trivial A period is coming only from the 0-1 term.
But actually, just you have some kind of heat equation, isn't it? Kind of heat equation. So what's the monodromy of a heat equation? You have just one equation, you have plenty of solutions, so
Yes.
depends strongly on solution.
Let me see. Okay, so maybe this, first of all, this formula is wrong. I have to modify it by adding this term. And you can show that, so if you take the product of that, then if you consider the differential equation satisfied by newly defined psi tilde mu, then it satisfies a similar heat type of equation, but without this term. So okay, so this last term can be absorbed by defining psi as a new tilde before coming from system. And this means that the partial differential equation for psi tilde is independent of nu. So shift from this is, again, so the analytic continuation is still a solution of the same differential equation, partial differential equation. So you have some, I'm not saying this is the basis of this infinite dimensional space, but you have some infinitely many labeled formal solution of this partial differential equation. And they are related by analytic continuation along A cycle or B cycle. Yeah. Then the important point is, so this B cycle monodromy is operator valid. So it can be reduced to the actual monodromy by taking the Zach transformation. So the Zach transformation of this
Maybe you can say that topological recursion gives you one specific asymptotic solution to this equation.
Yeah, you have distinguished solution.
Yeah.
So there are plenty of, well, it's not enough to find the solution. This equation is not enough to find the solution, but somehow you think that there is maybe another equation which fixes this particular one.
It is not giving, the monodromy is not a property of the equation, but it's a property of the solution which is provided by the equation. And then you will try to change it.
Yeah, so,
Yeah.
that's right.
Anyway, so this is one nice solution whose analytic continuation is still a solution of the same partial differential equation. And I take the Zach transformation. I'm omitting any other parameters or variables x and t. But then by taking this Zach transformation, so you can see that both A cycle and B cycle periods are diagonalizable, or I don't know how to do it. Yeah. This is very important because so now you have some formal series. Again, so this also can be written by some theta function series expansion, like this. At each it has this monodromy property. So first one is along A, and the second one is along B. Yeah. And this is some kind of formal series valued monodromy for formal series, but actually if you know about some arbitralization or exact WKB, then this kind of term-wise analytic continuation of the WKB solution gives some important information for the Stokes data or monodromy data. And those are nothing but the period. And in this sense, we can call those are some kind of Boros period along the A cycle or B cycle. And this is T independent by our construction. So now we have some isomonodromic type of formal object. And actually, so you can show that this one is a solution, formal solution of the isomonodromic deformation equation associated with Painleve 1. And as a corollary, you can find that so this Zach transformation of partition function is a tau function. So this is a story. Now, so I'm not explaining all the details, but basically this is one relation, one explanation why this is a tau function. Okay, in the last 15 minutes, I will try to explain about the relationship to the conformal block.
Okay, can you maybe comment? So this is a curve on C cross T. What happens on C star cross C star?
I don't know what to do, but
Yeah, but maybe you can comment on that because people are interested in that.
but maybe you know the answer. I think.
Yeah, but
I believe that Q-Painleve equation should appear from
yeah,
this
so you
conformal.
get difference equation instead of differential equation. And topological recursion can construct that.
I hope so. First of all, for example, Q airy or Q hypergeometric function, the forward to your result, but could you construct some formal WKB solution by your log topological?
I think we choose the zero curves first for yes somehow, but for hydrogens, there's no proof.
Yeah, maybe I think it's interesting to consider. Okay, but now let me focus on the relation to the conformal block. For the purpose, let me recall the key formula. this means this formula is somehow TR or WKB. Or this formula, which is obtained by gamma U, you will find irregular B here. This is that power function for Painleve 6 equation, but in this case I should take h by 1. So maybe you can introduce h bar, but maybe yes. And it is also written by back transformation. I use different parameter. Here you have set CFT, T, sigma is fixed by K. This one, when we, so this is the power function. Of most complicated second order Painleve. And this one, the CFT, is a bilateral conformal block. But to be precise, it is some product of band G functions, certain band G functions, times bilateral conformal block, which is usually written as this kind of diagram. And you insert certain vertex, regular vertex operator at 0, T, and 1 and infinity. And the sigma, which is appearing here, is an intermediate dimension here. Yeah. So this is the key formula, and this is bilateral conformal for bilateral 4-point conformal block, but again with central charge equal to 1.
Can you recall what was the G function?
So band G function. So this one is this one. Band G. And I'm not writing the argument, but the arguments are related, described by some combination of the momentum or some parameter of the vertex operator. So anyway, so this formula is very similar to that. And it's indeed, so from this, so you can imagine there is some close relation. So already we have seen some similarity here. So the topological recursion wave function and the BPC equations are similar, very. And also key formula also tells you the similarity. And let me show one diagram.
What was the spectral curve in this example?
Sorry?
The spectral curve?
Maybe you remember in hypergeometric I this kind of one. And in this case, another inversion. Sorry, I don't have space, but plus something, yeah, which is similar to the hypergeometric. But in this case, there is another term which is coming from so-called accessory parameter, which cannot be fixed by local monodromy exponents. But yeah, this is genus, and this is genus spectral curve. And if you run the topological recursion, you can obtain yeah, similar formula. In this case, so this spectral curve is, so YDX has only simple cells, simple poles, and in this sense, this is Fuchsian.
So B stands for Borel formation, or B of?
Yeah, so conformal rock free.
But is it formal, still formal thing, or Borel summed?
Conformal block is, this is a power series in T, for small t, and I'm setting H by 1. And actually, so this is somehow different expression of the, so we hope that, so this one is the Borel sum of the recursion partition function.
But Borel summed, I mean the...
I hope so, but there's no proof. Anyway, the diagram which I want to describe is, so here is a equation, and around that you have CFT, or gauge theory, or topological recursion, or topological string, and so on. And there are several approaches. So actually, so this one is gamma you will go and with this result. So you can construct a function by back transformation of the CFT conformal block. And irregular version is also proposed by Nagoya, for example, and many people. And actually, so these are related by so-called Alza, Topological correspondence, at least in regular singular. Well, this kind of bilateral usually conformal block is known to be related to the class of partition function. Yeah. Here you have Z safety, and here you have Z regular. But once again, the central charge is equal to 1, and in this case, epsilon 1 and epsilon 2 are related in this way. So-called self-real limit. And yeah, and actually, so these are also related by the so-called geometric engineering type of thing, and also mirror symmetry and BKMP conjectures. And I'm explaining this relation. And this one is Bertrand's book. And actually, so the recent preprints with Oleg and collaborators are trying to explain about this Yorgo, myself, and Rizobi, and are trying to establish this kind of diagram for irregular singular setting. This one is regular singular, but Painleve one is actually so irregular singular, so most irregular singular one. And actually, so in this paper, so maybe I can formulate one conjecture about the relation between topological recursion and conformal block in irregular case. Anyway, in this sense, so Painleve equation lies in an intersection of topological recursion and CST. And also it has some, maybe I forgot to write down one important also. So this one has some probabilistic approach. Probability. Like progressive evidence type of thing. I think so Painleve equation lies in the intersection of the main topics in this function. Yeah. Okay, so finally, so let me formulate one conjecture. So in our joint work, myself, Rizobi, Yorgo, what I discovered is several things. Actually, so my collaborator, Oleg and brilliant friends, could obtain certain algebraic approach to construct the irregular conformal block of half integer. I'm not writing down definition, but there is some construction, one of the new construction of the conformal block with some irregular singularity, with some runtime singularity. This is one thing. The other thing is I also studied the large T expansion of the topological recursion partition function. So as I said, so this Virasoro conformal block defined as a power series in T, which is T for small t. But the topological recursion partition function are defined as H buffer series. So they have different parameters for the expansion. To compare both, so for example, we have to know what is the large T or small t behavior of this topological recursion quantities. This is what we did in a second, and we compare them. And what we found is TR partition function, when t tends to infinity, in some sense, wait, I will explain what that question means, but up to some clear factor, so which can be also fixed explicitly, but you have this boundary function. S squared. So F is a fractional power of t, which I will describe later. And S will be 2h1 square, new square. And S minus k is coefficient. Yeah. And actually, so S is up to some constant. A fractional part of t. So this minus is not so you can forget about it. Yeah, and also so these coefficients dk are explicitly computable. For example, I don't have space, but so d1, for example, d0 equal 1. Or it depends on the choice of the normalization, but yeah. And d1 is given by I times u 94 nu plus 17 h bar square divided by 96 h bar square, and so very explicitly computable. And claim is that conjecture is that the right hand side is irregular conformal block of rank I over 2. Once again, central charge equal to 1. And after this the right-hand side has already proposed in bit earlier. Our paper appeared in 2019 in this year, but 2 years earlier, so Pog-Hossian already introduced this kind of irregular ramified conformal block. And so I can write down the meaning. Two Pog-Hossians, but slightly different spelling. Pog. Hossian and Pog. S-S-I-N. In 2000. What's this written? People. I'm not sure what is the relationship between. Anyway, so from here and this large T expansion. And actually, so this means that once again, so we exchange the expansion in T and expansion in H bar, and take the Borel summation of the H bar series in the coefficient wise. Then the leading term is given by boundary functions, which are similar to the DOZZ formula. And the other terms are essentially, this is polynomial in H bar in each step, so you don't have to take the Borel summation anymore. And we compare those coefficients up to S3 power maybe 5 or 6 to the expansion of computed by Minasolo. In this sense, also this can be seen. So maybe this diagram should still work in an irregular setting. And one question is, yeah, so actually,
So what happens with the spectral curves instead?
pardon?
What happens with the spectral curve and this T to infinity limit?
It's a good question. Actually, so one of the A cycle will peak.
So it's getting degenerate, and then it's somehow G0 spectral curve.
Yes, in some sense, yeah.
Is it absolute value of T going to infinity, or T going to infinity on some specific rate?
So this is a formal series, and I think on T plane, so maybe I took minus negative rate.
Because there are examples where there are different rays, and this asymptotic is completely different on that rays.
Maybe not completely different, but
This is about the function itself, but
yeah.
is supposing to have
Yeah. Actually, so there is another kind of expansion, but in this case, maybe S is replaced by I times S or something. So there is no big difference, but we just comparing the former series, both of the former series, and maybe they are divergent. And hopefully, we should be able to take the Borel sum of both divergent series and compare. So this should be the correct comparison of this duality diagram. But anyway,
Sorry, usually conformal blocks are expansions in forward of the position T.
yes.
And now why is this one an expansion in T to some fractional power?
Actually, in this case, I don't write down the definition of the conformal block, but in this case, conformal block is something like this. It is some irregular state of rank 5/2. It's not a usual highest weight vector. So usual highest weight vector is annihilated by positive beta from modes, but some of the positive modes can act non-trivially on it.
But still, I mean, all the descendants have conformal weights that differ by integers, right? Not by fractions.
it's not the position.
Yeah, not position, yes.
The angle of the safety position is with S.
But in the spectral curve, it looked like T was the position of the singularity.
No, here it's the one for Painleve 1.
I'm sorry, so this is a parametric case. So this is different from the regular singular situation. So T is appearing in the coefficient of the spectral curve. And I'm looking at the large T expansion of the topological recursion quantity. Then we recover this expansion, and it's coming from so this kind of irregular conformal block. And maybe it is out of time, but finally let me make a very brief comment about two things. So first one, I erased. But as I said, so after taking the that transformations, I said so exponential 2 pi I mu over h bar, 2 pi I rho over h bar are both periods. And actually, so if I assume several things, like Borel summability of each partition functions, and also some convergence of the discrete Fourier series for that transform, so we can look at what happened if some Stokes graph for this Painleve Y equation with some mutation. If some mutation happens, then so these variables are transformed in a cluster manner. So some cluster formation acts on it. And actually, so we could compare such a cluster transformation with a Stokes phenomenon for the tau function. And this is what I did with Marcos Marinho. So I mean that nonlinear Stokes phenomena for the tau function or irregular conformal block has deep relation to the cluster transformation. So this is what I did with Marcos Marinho. So I don't have time to explain. 2023. And the other final comment is, I also study, so this is a sequel 1 situation, but in sequel infinity, so we can also do some WKB analysis for the Hoyne equation instead of the Painleve equation. And then we can also try to relate both period in the Hoyne equation and the accessory parameter. And we could compare these expansions, WKB expansions of the accessory parameter in several irregular confluent Hoyne equations with the classical conformal blocks. It may come from the CFT, but it may not come from CFT, but we have some several checks, which is ongoing work with and Hajime Nagoya. No, I understood that he is one of my students. I hope to report it in some occasion, other occasion, but okay, I will finish. Thank you.
This DK, does this have like some combinatorial like description, like some?
Yeah. I hope to find that. But at least there is no some combinatorial or explicit formula. Yeah. So in this case, so this one can have a. So this is related to the Nekrasov partition function by the formulas, and it has some combinatorial expansion. And it's really of. I'm not familiar in physics computation, but some specialists say that this combinatorial expansion is obtained by some localization computation. But it is not available in this case. So in this case, the corresponding gauge theory is called Algeris-Douglas theory, and it doesn't have a Lagrangian description, and this is problematic in such an explicit computation. So indeed, it is not, some explicit formula is not known, but I hope to find it. If you have an idea, please tell me.
Nagoya is a person, right?
Not a city, yes.
So more questions? If not, let us thank the speaker again. We'll continue, unfortunately, without break. So the next speaker is
2-3 minutes maybe. Okay. It will be a little shorter.